Hello everyone. This video is for review of KSAT test. Admission year is 2024. KSAT stands for Korea Scholastic Aptitude test. This exam is taken once a year, usually it's on November. Okay, this time I want to deal with the probability problem, which is optional, all the time number 30. This is about normal distribution and using the standard normal distribution table with respect to finding the area of the probability density function. Okay, what's the point of this problem? The first point is standardization. When random variable has some normal distribution with mean m and variance sigma square, its probability density function looks like it's a bell-shaped symmetry with respect to this vertical line passing through M here, bell shape. The maximum value takes place at when x equals m. Here is a probability density function graph, and all the normal distribution random variable can be standardized as, let's say, call it a random variable z, following normal distribution with mean 0 and variance 1 here. So in this case, the probability density function for standardized normal distribution random variable z, its center is 0, is still bell shape. It takes the maximum value at z equals 0, and it has always standard deviation 1 here. In this case, standard deviation is 1 for the standardized random variable z. I'm sorry, I misspelled here. Standardization. I'm sorry. Standardization. It's right. So the random variable z is actually random variable x minus its mean value m over its standard deviation sigma. Okay. In terms of the area, we can say the area between random variable x probability, this area corresponds to probability of x having the value between m and m plus sigma. This value is the area of this shaded area here. It's a 1 sigma distance here, corresponds to the area from 0 to 1 here. It corresponds to probability, the standardized random variable having the value between 0 and 1 here. They are the same as the value or as the area. Okay. In general, let me comment one more thing. In general, when the area is far from the mean m, k times its standard deviation. Its distance is like this, m plus k times sigma here. This area, you can generalize it here. It actually corresponds to the area for the standardized random variable z having value between 0 and k here. They are the same as the probability or the area value. Okay. And the second point of this problem is that the area of the probability density function, let me call it briefly PDF here. It's a common abbreviation for probability density function. In case of, let me say, in case of standardized normal distribution random variable z, because any random variable with normal distribution can be standardized normal distribution with zero mean and variance 1 here. As I introduced, the probability density function for random variable z is a symmetry with respect to the vertical line passing through the mean value 0 here. It's symmetric. In general, with the same like length of interval, say for example this interval is 2 and this tail part here, let's say from a to a plus 2, say this probability for random variable z having value between from a to a plus 2, when this interval is located on the tail part. The other case, this interval contains its mean here. The ideal case is the mean is on the middle point of this interval, and its area will be like this. So roughly this probability value is getting larger, is larger than the tail part when this interval is more closer to its center. Center is z equals 0 here. It's roughly, I said. The specific detail one depends on the given conditions. Okay? So as an area, the area for the center when the interval contains its mean z equals 0 is roughly larger than the than when the tail, than the value when the interval does not contain its mean here. It's more biased to the tail part here. Okay. Let's go to the specific problem here. For the positive t value having this property, we need to standardize this random variable z to random variable x to z. Here z is equal to x minus its mean value 1 over sigma is t here, so over sigma. In this case, x minus 1 corresponds to 5 times t over 1 over t here. This is our random variable z. And this property is equal or greater than 1/2, which means this ending point, right end point here, for the random variable z is centered at 0 here, is symmetry with respect to this vertical line passing through the 0 here. Okay, looks good. So its right ending point, let's say this is L. When right ending point L is positive here, this probability value corresponds to this area here. Actually, the area for this half is 0.5 and this half is 0.5 here, as you already know. So this L 5 times t minus 1 over t should be non-negative here, which means t should be equal or greater than 1/5. That's the condition for the positive t here. And second, for the second, we deal with this probability, which depends on the value of t, and we want to know its maximum value here. So let's standardize this random variable x by the same method, and then we'll get t squared plus t over t. 1 is cancelled here, and t squared minus t over t, this probability, and in the term of the new standardized random variable z, it corresponds to the probability for the random variable z having value between t minus 1 and t plus 1. And you can observe that this interval from t minus 1 and t plus 1, the length of this interval is 2 with center, its center is t here. And then, by the way, by the condition for the positive t, t has the value at least 1/5 here, at least 1/5. Okay, so that means where is 1/5? This problem is rather simple one. There's not complicated setting, but we have one setting for the positive t value here, and all the things that you need to know is how to standardize the normal distribution to the random variable z, and what the probability density function of z has properties, what kind of properties it has. As I said, it reaches to a maximum at z equals 0, and it's a symmetry with respect to a vertical line, z equals 0. So to get its maximum area, the continuous interval should be, the center of the interval should be close to the mean of this standardized random variable. Okay, that's it.